So we are in a position now to define simplicial homology. So the main thing we are not going to prove here is that this is a topological invariant. Also, it's not really functorial. I mean, it could be functorial in a more restricted category, etc. But this is really quite useful anyway if you are, for example, applying algebraic topology, because it is a topological invariant and does coincide with singular homology or any other homology that you would typically like to consider. So if you're actually working with algebraic topology, this is really useful. It's also a warm-up for when you learn singular homology, if you do. Okay, so what is the simplicial homology? Let's start with sigma as simplicial complex. Remember, it has vertices and so on. And well, it could have a vertex, an edge, a loop like this, and maybe another loop, and this one fills up a triangle. But if you remember, we had to pick directions for edges to decide when to give a coefficient positive sign and when to give it a negative sign. Similarly, for a triangle like this, I'll have to pick an orientation, whether I want a positive to be clockwise or anti-clockwise. Of course, clockwise and anti-clockwise doesn't make sense unless it's in the plane, but still, which way is positive, which way is not. So for that, we pick an orientation, as it is called. This is a little different from the usual orientation, but related to it. It's more data than that. It determines an orientation. So orientation is the following: for each sigma as V0, Vn, so given any n simplex in sigma, we fix an order. So an order, by which I mean a total order on V0, V1. Okay, and this has to be consistent. If tau is contained in sigma, order on sigma gives order on tau. Now, an easy way of doing this is to simply order all vertices and then restrict to various simplices. But there's no need to assume that that is how it was done. So if you want to see how do you know orientation exists, that's an easy proof. Just put a linear order on all of VI's and then simply restrict to all simplices. Okay, so some bit of notation. So if V0 Vn, we look at simplices like this: sigma equals V0 Vn. Simplex means sigma. So let me not call it again sigma. So it means firstly the set V0 Vn, and all of these are distinct. This is how I write it, belongs to sigma, and V0 is less than Vn in sigma, meaning in the order on the vertices of sigma. Okay. So there is a unique way in which a simplex can be written in linear order like this. So we avoid multiple counting sigmas, and it will turn out it also gives us an orientation. Okay. So with this as a background, we can define a boundary which generalizes what we had. So remember that if I have an edge and I had E like this, and this was V0 and V1, the boundary of E would be equal to V1 minus V0. Okay, and let's take a triangle. Perhaps we'll draw straight lines between the vertices. So I have a triangle like this. I have a straight line here. I have a straight line here, a straight line here, and a straight line here. Okay. Sorry, it seems determined not to fit. Straight line here, a straight line here, and a straight line here. And let's give these, remember, names. And I'll call them V0, V1, and V2. And assume, of course, that V0 is less than V1 is less than V2. Then you think of this as being V0, V1, and V1, V2, and the edges are oriented this way. And we'll think of this simplex as being oriented with a boundary like this. You'll see that in the formula. Okay, so what we'll want is, if this is sigma, what we will want is boundary of V0, V1, V2 is going to be the first edge, V0, V1. Okay, And then we have the second edge V1, V2. And we'll write it in a different order, minus V0, V2. Okay, so we would want the boundary to be this way. Because we have taken a total order, we are forced to have this. This is what it corresponds to geometrically. And so given this background, what are the chains? Chains were clear. So let's fix R a ring. We'll be a little more general. So example, R equals Z. And well, there are other couple of examples which are important. You either look at rational numbers or real numbers in some cases, or integers mod 2. Integers mod p are also important in many contexts. Many rings are important, but this is going to be the default. Okay, so if not specified otherwise, we will take it to be R, and we'll define the Ck of sigma is the free abelian group if R is Z, but in general free R module on the K simplices. Okay, let me of sigma. This is exactly generalizing the C0 in C1 we took earlier. And we have to define a boundary map. So del K, which maps Ck of sigma to Ck minus 1 of sigma. Note we have to get the sign correctly, and the correct notion of sign is so that if I took del K of V0 Vk, I get various K minus 1 simplices from I equals 0 to K. I look at various simplices. I should give myself some space here. The space will be for the sign. The simplices where I drop the ith entry for various I. And you see if I drop V1, I get a minus 1 sign. And if I drop V2 or V0, I get a positive sign. So from which you can presumably guess that this is the boundary. Okay, so what's so great about this formula? There is one key property that we will see about this formula. Okay, but first, that's a simple formal calculation. You don't have to look at the picture for that property, though it might be fun to look at the picture and see what is happening. But this formula corresponds to this picture, as you can see. So the key picture, key result about the boundary that lets us define homology. Let me state it here, and then we'll look at a degenerate case at 0. So theorem is that if I look at delta k minus 1 composed with delta k, that is I take the boundary of the boundary, this is going to be 0 for k greater than or equal to 1, where it makes sense. Okay, so if you take a triangle and you take its boundary, it's going to be this edge, and this edge, and clearly the boundary of that is 0. Okay, in many cases this appears, even this is analogous to div and curl and grad and curl and so on, various combinations being 0 as well in Stokes theorems and related results, divergence theorem. So we have del k minus 1 composed with del k is 0 for all n. Okay, so this remember is a map from Ck. So let sigma belong to Ck, and let's write sigma as V0 Vk. Oh, not every element of Ck is of this form, but it's a linear combination since we are talking about free module with this as a basis. So it's enough to show that the boundary of these is 0. Okay, so let's look at delta k minus 1 composed with delta k of sigma is delta k minus 1 acting on the sum I is 0 to k of minus 1 to the I, and we have V0, Vi deleted, and Vk. So that's great, but now we want to take the boundary of this. Well, we might end up deleting before and after, and the sign is a bit different in the two cases. So let's split this into two cases. J, well, it can't be I is already deleted, so J goes from 0 to I minus 1 is one of the cases. And I'm looking at the boundary, so I'm looking at the boundary term of, I'm putting this del k minus 1 inside here. and looking at the corresponding boundary terms. So when I look at these, then I get -1 to the I, which was there previously, and -1 to the j. Okay, and we have deleted jth term from here. So we are looking at v0, vj hat, vi hat, all the way to vk. Okay, this is one set of terms. And then we have another set of terms, and this time we are going to take j equals I plus 1 to k. And I'll have -1 to the I. But you notice that if I delete a term here, I was previously deleted, so its index has been shifted down by 1. So it's -1 to the j minus 1 of v0. This time vi comes first, and then vj hat. Okay. Now to compare the terms, we are going to interchange. I'm sorry, in both cases I also have a sum. I is 0 to k. And here too I have a sum, I equals 0 to k. So to make these easier to compare, I'm going to interchange I and j here. Okay, so interchange I and j and change the indices accordingly. Now the first term can be written as the double sum where j is before I. 0 is less than or equal to j, is strictly less than I, is less than or equal to k. And -1 to the I plus j, v0, vj hat, vi hat, and vk. Now the second term was different earlier, but when I've interchanged I and j, now j is what was previously I, so it's between 0 and k, and I is bigger than j. So it's the same indices. Again, we are looking at 0 is less than or equal to j is less than I is less than or equal to k. And again we have the same case, v0. vi hat has now been renamed vj hat, meaning we have not changed v's, but the index is j. And this guy is vi hat, so these look the same, vk. Now what has not changed is this is -1 to the I and j minus 1 has changed, but nevertheless this is I plus j minus 1. Okay, this was -1 to the j, -1 to the I minus 1, but since addition is commutative, you can get this. And so of course you see now that you have a double sum. 0 is less than or equal to j is less than I is less than or equal to k of some things times v0. We have dropped vj hat and we have dropped vi hat. And as you probably have spotted by now, the first one is -1 to the I plus j, and the second one is -1 to the I plus j minus 1, and this is of course 0, so we get a 0. Okay, so this is the technical result that we have, that is boundary of boundary is 0. Okay, it's crucial, and it's a simple calculation. It really should be interpreted as saying we have got the notion of the boundary correct, that we have this kind of result. And having got this, we can now define homology. Let's just define c minus 1 equals 0, and this is the 0 module over R if you wish, and delta 1 0 is the 0 map. It has target which is 0, just for completeness. Sometimes you don't want to do this, what is called augmented homology, but for the present we have these things. Okay, so before writing the definition, let's note that del k composed with del k plus 1 is 0 for all k, okay, greater than or equal to 0 now, because this gets a 0. So this implies that the image of del k plus 1, okay, so these are going to be called the boundaries, bk plus 1 or bk, I don't know which one you'd like to call it, is contained in kernel of delta k, which we previously called zk. Okay, so definition is this thing is there. So then we can define homology of sigma is the kernel of boundary k by image of boundary k plus 1. Okay, so the image of boundary k plus 1 comes as in the previous examples, that if I have, say I had 2 loops, but I filled one in with a rectangle, then this thing has to become trivial. Okay, that we get as the homology. So we have defined simplicial homology. All that remains to be done, or all that we are going to do now, is first compute for some examples by hand. Then we will look at a version called delta complexes, which are simpler than simplicial complexes. I mean, more complicated to define, but as a result, a given space can be represented more easily by them, and show how to adapt to those, which is straightforward, and then compute more examples using that.